This is Bang Goes the Theory. Jem is back in his workshop doing more extreme engineering. Whoa! Liz is going back to the lab to bring you the latest research. And I'll leave no stone unturned to try and answer science's big questions. That's Bang Goes the Theory, putting science to the test. And welcome to a new series. It's great to be back. It's great to have you back. We never rest. Coming up on tonight's show, Jem is going to try and break a land speed record with a fire extinguisher. And I'm going to talk to a man with a beard about our impending oil crisis.
Hi, Rich. Nice to meet you. Thank you very much for talking to us.
But first up tonight, we've all watched them, those slick American cop shows that use crime scene investigation to catch the bad guys. But how close to reality are they? Well, I went to find out. Nowhere quite as glamorous as Miami or New York. They sent me to Lambeth. Our reconstruction starts at midnight with a burglary in a residential street. It looks like a clean getaway, but vital clues were left behind. We've identified 3 suspects, this bunch of reprobates. So we're going to turn to the world of forensic science to try and work out which one of them is the most likely culprit. Our forensic team visit the house, and although they find no trace of fingerprints or DNA, they do recover other compelling evidence. Helping me unlock all these clues is Dr. Sarah Jacobs from the Forensic Science Service, Britain's leading crime scene investigators. So Sarah, how are we going to approach this case?
I know your crime scene examiner recovered glass from around the break in the broken window. So we're going to look at the suspect's clothing to see if there's any fragments of glass which could have come from the window.
Okay.
Obviously then giving support that they were present at the time the window was broken.
Good stuff. Police have seized the tops they believe the suspects were wearing on the night of the burglary. Sarah gets me brushing down each of them in turn over this huge funnel, dislodging any microscopic fragments of glass and then catching them in a Petri dish underneath. Ooh, pretty impressive.
You see there's quite a lot of dirt there, so there might be some just general dirt. There's also some quartz there, probably, a bit of sand.
And hopefully some glass.
Yes.
We get a result. Small shards of glass are found on just one of the suspect's tops. The next stage is to compare those shards with those from our crime scene by measuring the refractive index of the glass.
That is a technique that measures the speed of light as it goes from air into glass.
Okay, so presumably the refractive index of different glass will be a different value based on the way the glass is made?
Yeah, it's based on the chemical composition. If you've got slight changes in chemical composition, maybe the way the glass was mixed.
The speed and angle at which light passes through the pieces of glass found on the suspect's top is analysed. That information is fed into a computer that calculates the refractive index of the glass. And it's a perfect match for the smashed window. This is strong evidence that one of our suspects was at the very least present when the glass was smashed, but we need more. So next we turn our attention to a series of fibres found on the edges of the broken window pane. Could they have been left there by one of our suspects? Fibres look incredibly distinctive under the microscope, so identifying fibre types is relatively easy. Wool looks scaly, cotton looks flat and twisted, while synthetics like polyester and acrylic look smooth and regular. It's soon clear that our crime scene sample is blue cotton, so we can dismiss one jumper made of black wool straight away. The 2 remaining tops are both blue cotton, but closer examination under different frequencies of light reveal that one of them is clearly the wrong shade of blue, meaning that too can be dismissed. But are the fibres from the 3rd and final jumper an exact match to the crime scene sample? Dye analysis by liquid chromatography gives us our answer. Precisely the same chemicals are present in each.
It's a really, really good feeling when you're getting results, isn't it?
It is, yes. So
Excellent.
that top is a potential source of the fibres.
You see, you're
at the
still just
scene.
saying potential. I'm like, that's it, that's the guilty party. Why is it still just a potential
Because they
result?
they're blue cotton fibres. There are other sources of blue cotton fibres in the world.
Okay,
so we can't
fair
say
enough.
conclusively that jumper has left those fibres.
But again, with other evidence, this all adds to pointing at a particular
Exactly, it's
suspect.
building up a picture.
And the last part of that picture will hopefully come from the robber's feet. Crime scene investigators found the impression of a shoe on the wooden floorboards of the house. And this could tell us almost as much about the robber as a fingerprint.
So this is our gel lift that was recovered from the scene.
Yeah.
The first thing that I do with that at the lab is I photograph it. The next stage is we want to identify the type of footwear that might have made that mark. So to do that, we use our footwear intelligence technology.
The Forensic Science Service has a massive database of hundreds of different sole designs. By searching for different pattern characteristics, it doesn't take me long to find the shoe type that matches our footprint. And one of our suspects owns that very same style of shoe. Using aluminium powder, I can make an impression of it to compare it directly with the crime scene print.
Yeah, that's fine.
Something immediately catches my eye. The two appear to share a deep cut in one of the studs, presumably the result of everyday wear and tear. A quick check of the sole itself confirms my suspicions. Our suspect's shoe seems to match the crime scene footprint. But I'm getting used to this forensic investigation malarkey, and I'm fairly sure I can come up with a get-out-of-jail-free card.
Say if the suspect says, yeah, these are my shoes, but I actually only bought them yesterday. I did not have them in my possession. I did not own them. The date of the crime.
Well, there's a technique that we can use called the Cinderella technique. So what we would do is we have a photograph of some insoles here. We then photograph those at the laboratory using infrared lighting. And can you see you've got a really nice impression of the bare foot there.
Okay.
And that's going to be quite distinctive in terms of the position of the toes, the position of the arch. So that's going to be fairly characteristic to that person.
So the important thing here is these kind of impressions don't get made in a couple of days.
No,
It takes a while.
these would indicate that that person has regularly worn those shoes.
You've got all bases covered, haven't you?
On their own, no one test result is conclusive, but together, the evidence is compelling. The same suspect was implicated in every test. He was covered in shards of the same type of glass that was smashed. Fibres that matched his jumper were found at the scene, and a footprint that could only have come from his shoe was left on the kitchen floor. So, only one question remains. Who is suspect number 3? Jan, Dallas, or Jem?
So go on, Liz. Who was it?
Well, going on the mugshots alone, I would have said him. You looked well shifty in that photograph. But after all the CSI, I think it was this guy.
I always knew he was dodgy.
Absolutely.
say.
Even without any biological evidence, no DNA, you can still get the bad guy.
I love detective work.
That's scary, though, isn't it?
But moving on, Dallas,
Yeah.
have you ever been stitched up by a mate who's found some footage of you where you look a little bit stupid?
No.
Really?
I can honestly say that's never happened.
Interesting. How about this for the first time?
Oh, no. That's a little bit embarrassing.
That's really annoying. No, you know what that was? That was a failed attempt at demonstrating Newton's third law of motion. Every action doesn't necessarily have an equal and opposite reaction. Although I knew I'd done wrong after you explained it to me in detail. So,
It was the single worst fire extinguisher on an office chair demo I've ever seen.
Yeah.
But it did get me thinking, what is the fastest anyone's ever gone powered by fire extinguishers?
no idea.
Turns out, Jeremy Clarkson got 8 of them strapped to a buggy and managed 28 miles an hour.
Okay.
It's not bad.
It's not bad, but I reckon we could smash that record using just one single office fire extinguisher.
In your face, Clarkson.
These things contain a truly staggering amount of high-pressure gas. most of us will probably never pick up anything that can release energy more quickly. I'll show you what I mean. On with a couple of specialist fittings. Length of high-pressure hydraulic hose, a length of steel tube, and one very brave parsnip. Parsnip has to go all the way into the tube. Goggles. Ear defenders. 3, 2, 1. Whoa. Yeah, as I said, a staggering release of power. Getting that parsnip to warp speed only used a tiny fraction of the gas in this cylinder. That's because when I squeezed it in here, I made quite a tight-fitting root vegetable piston. And pistons are the most efficient way of getting movement out of high-pressure gas. So if I want massive acceleration, I'm going to have to attach myself to the end of a long piston. And the way I was thinking of doing that was like this. So, the gas goes into one tube, I attach myself to the other tube, I'm gone. It's vital to keep the go-kart chassis light and strong. So, lattice steelwork seems to be the best bet. The biggest worry is the pipes sticking together on launch. If they do that, they could turn into a bomb. 95% done now. Lightweight steel frame, racing seat, so maybe I can handle the G-forces, and this, our big sleeving piston. Now, when I hit the accelerator pedal, it's going to end up squeezing the trigger on the fire extinguisher. That sends high-pressure gas down into the end of the 2 sleeving tubes. I come to the back. When that happens, these 2 are going to want to sleeve apart like that. But if this is fixed to something that just can't move, it means that whole rig goes that way. But we'll only find out if it can handle those kind of forces if I actually test it. I just hope I don't scream. This is going to be quick. 3, 2, 1. No way! Oh, man. There's no brake in there at all.
That is crazy acceleration for just an office fire extinguisher.
And I am actually pulling 3.5 G on launch.
Which is space shuttle. More than the space shuttle.
Yes, indeed. And that's why it feels just absolutely crazy. But what happens is I get to 30 and the efficiency of it just dies.
Why?
Because I'm just venting gas out the back at that point.
So
I've not got the tubes.
What's the answer?
Second stage thrust.
Nothing like a bit of second stage thrust. Before we get to that, though, time to catch up with Dr. Yan and his latest adventures in science. Now, this week, he's messing about with Marmite, which personally I think is the work of the devil, but go figure.
Have you ever wondered why clouds are white? Well, I'm going to show you by making this go white. Well, pale brown at least. It's just ordinary Marmite, but you can try it with Bovril or even Vegemite if you're Australian. You see, it's pretty brown. And all I'm doing is whisking it with a fork. Just give it a bit of a beat there. Can you see? Whisking, 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 whisking. Look, you see it's changing colour already. Yeah? That's quite cool.
It's like chocolate.
Definitely a lot paler. You seen Marmite like this before?
No.
Do you want to go? Do you want to try whisk? See if you can make it go white yourself. Yeah. Go on, and I'll put some into here. There you go. Try whisking it and see what happens. And I'll have a go as well. Okay. Right, let's put some in there. We'll get you to put some whisking in there. Any idea what's going on here?
No, none at all.
Is it the air?
Exactly. So what's happening?
Beating eggs, and they go. Yeah.
It's exactly like beating eggs, that's right. I'll cheat. you're putting lots of tiny little bubbles into it. It might not look like it, but this Marmite is actually going foamy. Before, the light that was around us, when it hit the Marmite, it was mostly being absorbed into it. The very little that came back towards our eyes made it look, well, very dark brown. Each air bubble that we put in here, though, scatters light a little bit. And so the more air bubbles there are in there, then the more the light is scattered, the more comes back towards our eyes and the paler it looks.
Right, so if you keep whisking it, it's going to keep going even
lighter. It goes lighter and lighter because it gets more and more air bubbles in it. And so it's just like, you know, a pint of beer. Well, the head on a pint of beer is creamy, no matter how dark the liquid is. Yeah? And that's because all the bubbles in the foam make the head look that colour.
What's that got to do with the clouds?
Well, they're made up of tiny little droplets of water. So rather than air bubbles scattering the light, it's those tiny drops that do. But it's still the same scattering effect that make them look white. Do you want to see if it tastes the same?
Sure.
Oh, yeah.
I'm going to take him home before he eats it all.
Does it taste the same?
Lovely.
You really are dreadful.
No. Thank you. This is crude oil. Now, we're currently getting through something like 85 million barrels a day.
A day?
A day of this stuff. But the big question is, what's going to happen when it runs out or we can't get to it anymore? Now, a generation or so ago, the only people really worrying about peak oil were yoghurt-weaving, beardy hippie types. Not much has changed, actually, except one of them now does own 38 long-haul jets. And some trains.
Hello. Hi, Rich. Nice to meet you. Thank you very much for talking to us.
Pleasure. Can we just talk a little bit about peak oil as a definition? Because I don't think it's one of those terms that everyone is entirely clear what it is.
It potentially is when the demand for oil exceeds supply.
Right.
And 5 years from now, there is a danger that demand for oil will exceed supply. And countries all over the world will be scurrying to make sure that they get their oil.
Yeah.
You've got now China growing at 10% a year, India growing at 9% per year. I mean, hundreds of thousands of new cars coming on the road. In that scenario, oil prices could literally go through the roof.
What happens if we do nothing?
I think if we do nothing, the recession that we've just been through in the last 12 months will look mild.
Now, I don't want to be alarmist, and let's just be clear here. Oil's not going to run out today, tomorrow, or even next year or the year after. But a lot of people now are predicting in the near future, as oil becomes more and more difficult to extract, the price is going to go up, and that is going to cause problems for everyone. So, if we do reach peak oil soon, this point where demand outstrips supply, how is it going to affect us? Well, you might think that it'll just put up the price of fuel in your car. Well, you'd be wrong, because oil is involved in everything that we use, from the plastics on this dashboard to the fabric of the seat to the paint of this car to my jacket even. It all relies on oil. The tyres of this car need oil, and even the roads on which we drive is made of the stuff. And it doesn't end there. This is a wheat field, and it takes something like 3 tons of oil just to get 1 ton of wheat to your plate. And what about meat production? For that, you're looking at around 1,000 litres of oil per 350 kilograms of beef. And that's a problem. Oil is perhaps the ultimate non-renewable resource. To understand why, you have to know how it's made. And it really boils down to these little guys, plankton and other tiny marine organisms. But how do you get from these little guys to this stuff, oil? Well, first up, our little friends here do what they do best during the day, which is absorbing CO2. And then, about 150 million years ago or so, they die. And as they sink to the bottom of the sea, they're very quickly covered up by sand and mud. And it's important to be quick, so we don't want them to rot away in the presence of oxygen. And over millions and millions of years, the sand and mud builds up and becomes sedimentary rock. And as the pressure increases, it actually cooks in a geological kitchen. And our little friends get to about 100 degrees or so, cooking away nicely. And millions of years later, voila, hydrocarbons, or oil. All we've got to do is find it. And that's getting very hard. After 150 million years or so in this geological kitchen, most of the oil is thousands of meters under the ground. And that's the stuff that's easy to find. Nowadays, new oil finds are mainly turning up in smaller and smaller pockets way out to sea, and that's why it's getting more expensive to get at.
How much does it cost to sort of take a platform out and, drill for oil for the day?
The first thing to say, this doesn't get it out of the ground. This is actually the expenditure that's made to try and find the oil. This is just the first stage.
So this isn't even this isn't getting the oil, or this just finds the oil.
This just finds the oil. A rig like this would cost a few £100,000 per day. More specialised rigs would potentially cost £1 million. So we're spending several £100,000 a day sending this out to the North Sea to find the oil. 1 in 10 chance probably in the North Sea of finding oil.
Oil has always been hard to find simply because of where it's trapped, thousands of meters under the ground. So hard that no one really knows how much we have.
Is there a sort of figure of here's how much oil there is in various locations?
There's two figures. One is all about reserves. Reserves are oil that we know we can get. And then there's a hypothetical number, which is called resources, which is oil we may be able to get one day if everything works well. So in terms of reserves, these people talk about the 1,000 gigabarrels, but these numbers are bandied around and they're changed, and governments may or may not release the exact correct number.
With so many unknowns to factor in, we can't be sure if Richard Branson's claim for oil shortages coming within the next 5 years are accurate or not. What we do know is that we're seriously addicted to oil. And it might give us pleasure now, but if we're not prepared, as we're forced to wean ourselves off it, our lives are going to become very painful indeed. This is a biggie.
Yep.
Seriously, if we don't wake up and actually admit to ourselves that we've got an issue, we're in a heap of trouble.
Absolutely. The problem is we still rely on this stuff far too much. This is definitely a story we're going to come back to.
Definitely. Jen?
Now for the conclusion to my high-pressure extravaganza. How fast can one man, one cart and one fire extinguisher really go? My first test showed that by sleeving 2 tubes together, when I fired my fire extinguisher, I could easily burn up a Ferrari for 3 meters. Okay, looks like I can get off the line pretty quick, but once those tubes have separated, I've still got loads of carbon dioxide left in my fire extinguisher and nothing solid left to push against. Now, I could just dump the gas straight out the back, but that's pretty inefficient. We had to go back to the drawing board and come up with a new solution. One that would keep me accelerating. Right. I had an idea worth testing. I'd use our high-pressure gas to squirt water.
Let's take out the pin.
That's all right for thrust. Scaled up, the idea is to fire the remaining CO2 in my fire extinguisher into a 90-litre barrel of water. The vast pressure of the gas should force water out of this nozzle at over 300 kilometres an hour. From my calculations and experiments, I'm confident that that will give me a hefty 50 kilos of thrust right to the end of the track. But when I tested my barrel, I discovered a potentially lethal problem. Its thick steel walls couldn't quite take the 120 tons of force that full fire extinguisher pressure exerts on that tank. So, I've got to make sure that the exit nozzle is exactly the right size, that the pressure never gets that high. Hence, all that maths. If my numbers are good, this is going to be brilliant. If they're wrong, this is the last test I'll ever do.
3, 2, 1, fire.
The The massively good news about this is nobody died, no buildings were destroyed, which means I now feel confident I can strap this to some homemade vehicle and it's not going to blow the back of my head off. Let's hope it's the same story at the racetrack tomorrow. Remember, Jeremy Clarkson did 28 miles an hour with 8 fire extinguishers, so that's my target. Anything less will not do. Yes, Bangos the Theory are the winners. This is high pressure action. As soon as I release the CO2, the pressure in the 2 tubes under my seat hits a terrifying 60 atmospheres. That's enough to give me a good kick off the line. But as soon as those tubes separate, the thrust drops dramatically, and that's when I fire the CO2 into the water barrel. Suddenly, the water jet is being pushed out of the back by a massive force. And it's that sustained thrust that's fired me down the track and into the record books.
43 miles an hour. Well done you. That was amazing.
That's really good. I reckon that's possibly, maybe, perhaps some kind of record.
Just off 1 fire extinguisher.
Yeah.
Fine.
Right.
Very small thing.
Small, just the smallest thing ever.
Like what? Like atoms?
Yeah, exactly. Sure about this?
No, but it might just be the future of skateboarding.
Good luck, Jemothy.
Maybe it won't be the future of skateboarding. Right. Yeah. As you can see, this is not something to do at home.